In this video, we're going to talk about a function that has a particular base e. The number e is a number similar to the number pi in that it's an irrational number. In other words, it's a decimal number that never ends nor repeats. But for approximation purposes, you can say that e is approximately 2.71828. Now, to derive the value of e, you would actually have to take a calculus course and see it derived. But I can tell you that the number e actually comes from a couple of different expressions. But one expression would be if you took the function 1 plus 1 over x raised to the x power and you let x approach infinity, then this function would actually converge at a value, and that value would be approximately 2.71828, but it turns out that value is just that number e. Okay, so I won't talk anymore about the development of the number e's, but let's talk about graphing this function e to the x that has this natural exponential base, which is what this e is. This is the natural exponential base. Okay, so if you plugged in, you could just grab your calculator and then find out what is e to the x when x is negative 2, negative 1, 0, 1, and 2. And I'll just round these to 2 decimals. So when x is negative 2 on the calculator, e to the negative 2 comes out to be 0.14. E to the negative 1 comes out to be 0.37. E to the 0 is 1. E to the 1 is approximately 2.72. And e squared is approximately 7.39. So if you were to take some graph paper and plot those points here, this would be, negative 2.14, negative 1.37, 0, 1, 1 and 2.72, and then 2 and 7.39. And then if you connected those dots, it would actually give you this graph right here of e to the x. So that's what the graph of that function looks like. And you'll notice it looks very similar to the graph of 2 to the x. And if you wanted to graph some variations of this function, like let's say you wanted to graph minus the function e to the x minus 2, well, since I'm replacing x with x minus 2, that would just shift the function to the right 2 units. And then the minus here would reflect it about the x-axis. And I can show you that on the graph here. So if you look at this graph here, let me move my grid back down here. So if you look at this graph here, you'll see this is y equal e to the x. And then if you were to take this graph and shift it 2 units to the right, it would just kind of move it over here a couple units. And then when you multiply it by negative 1, it would take this graph and reflect it about the, I'm sorry, I've got the wrong one drawn here. My exponent doesn't want to operate properly for me. There we go. Okay, so if you were to take this graph and shift it 2 units to the right, that would kind of move it over more over this way. And then when you multiply it by negative 1, it actually reflects this graph about the x-axis. And so again, take this graph, shift it 2 units to the right, then reflect it about the x-axis, and you get this graph, the graph minus e raised to the x minus 2 power. Since you already saw that one that I had mistakenly put in there, let me go ahead and show you what that would do. That works a little bit different. For that one, this one would actually you would actually reflect the graph about the x-axis first, because you'd have minus e to the x. So that would give you a graph that opens down here, and then the minus 2 here would shift that graph down 2 units. So if you took the graph that went like this and then moved it down 2 units, you would get this graph here. So again, that's not the one on the paper, but I just wanted to show it to you because the this technology here gave me that one by mistake. Now if you wanted to graph this one, since you're replacing x with negative x, it would actually reflect the graph about the y-axis, and then the 2 stretches it by a factor of 2, and then the plus 3 would shift it up 3 units. So I'll go ahead and show you that. So here's the graph of the result, but let me kind of show you how that graph comes about from this graph step by step. So let me take away a couple of things here. So if you take this original graph and reflect it about the y-axis, you get this new graph, and that new graph is e to the minus x. Well then, if you multiply that graph by 2, it gives it just a little bit of a vertical stretch, so it kind of stretches it up just a little bit. And then when you add 3 to that, that actually shifts it, shifts the entire graph up 3 units. So that's how you get that graph. And now again, on these transformations of graphs, and nowadays you don't really have to rely on them so much since we have all this graphing technology, but I still think it's good to understand how these operations affect the graphs of functions. Okay, the last thing here is just 3 little exercises here. You can do these on your own and just make sure that you know how to evaluate exponential functions on your calculator. Now remember, the domain of exponential function is all real numbers, so I should be able to evaluate an exponential function at any real number. So I've given you kind of some weird numbers here, but let's start with the function 2/3 to the x power. If we evaluate that at square root of 11, 2/3 raised to the square root of 11 should equal 0.261. And so just make sure that you can actually get that answer rounded to 3 decimal places. Now here is a function where I'm using t for the independent variable. So s of t is equal to pi to the t power, and it says evaluate this at the number e. So I'm evaluating it at that number e. So take your calculator, and you should have a pi function on your calculator. So put in the pi function, then hit your exponent button, and then find your e button, and then hit enter, and that should give you 22.459 rounded to 3 decimals. And then this one, I'm going to take 10 times e to the 1 minus x, and I'm going to evaluate this function at negative 0.05. So if you plug in negative 0.05, you'll actually get 10 times e to the 1 minus negative 0.05, which ends up being 1 plus 0.05, or 1.05. So you end up getting 10 times e to the 1.05, and that gives you 28.577. So again, just make sure you can evaluate these functions on a calculator and get the right numbers. Okay, so that ends the section on exponential functions. So in the next few sections, we'll be devoted to log functions.